Hello again. In this video I'm going to be taking you through an air standard diesel cycle. This problem is problem 9.26 in the book. If you need to see the constant values, just stay here for a second and then move on to the next part. So to begin this process, we are going to find the values associated with state 1. State 1 is at the beginning, the beginning of the compression stroke of the 4-strokes engine. So we are, as it says, finding state 1 values. So from the tables, I think for this problem, I think it's an English unit, so let me pull open the book. I'm trying to find the table to use here, but it's from the air tables. Let me see if I can find the exact name of it, since I neglected to do that during the actual process. This is table A22E in your textbook, and that's what we'll be using for this problem. And so you find, once you use the table, you can get U1 to be 88.62 BTUs per pound, and VR1 to be 158.58. Drop that book. Alright, and then from those two values, well, I guess from VR1, you're now going to solve for something at state 2. This is, I guess you would say, fixing state 2. So you're fixing it at a certain value, and you solve from that value. And so, for this one, you are using VR1 and the compression ratio to solve for something at state 2, which would be VR2. And the equation used here is VR2 over VR1. One sec, did I get it right? Oh yeah, it's VR1 over VR2. Always confuses me. I just know that the volume has to drop here. That's how I know. So VR1 over VR2 is equal to R. So it doesn't matter if you know the equation or not, because if you know your volume at the bottom is a lot bigger, and if your VR2 is bigger than VR1, you know you did something wrong. You just kind of have to know the problem, and you know what's changing. So that's how I always do it. But I mean, if you can remember the equation, by all means do so. I just can't for some reason. So you get VR2 to be 9-911. And from this value, you are now going to go back into the table, A22E, and solve for H2, or it'd be H2. These problems always confuse me. Instead of U's and H's, yeah, it's not like the auto cycle where you just use U's. But in this one, using U2. See, I wrote U2, but I think I find H2 here. So, yeah, see, it confuses me. Let me see if I did that right. Always rewatching this and adding voice to it. A little difference. Yeah, see, H2. I caught myself. See? So H2 and T2. T2 isn't, well, in this problem it is necessary, but in other problems it might not be, depending on the information given. But for this one it is necessary. So the way I suggest doing it is, in these problems, make sure you try and find everything you can at every state. Even if you think it might be, useless information, it could help down the road and save you some time. And so we find that H2 is 369.843 and T2 is 1502.51. How's a bad circle? They don't teach you that in engineering, how to draw circles. Let's stick to boxes. So, from here, we are now going to solve for something at state 3. So we're trying to fix state 3 using some equation, using our unknowns that we have at this point. And so we're trying to find something like a VR3, temperature of 3, H of 3, something like that. But for this problem, because we are given a certain set of information. Like I said, these problems change drastically depending on what is given. So, I mean, just bear with me on that. But for this part, we have T3, or we have T2, we have R, RC, and T2. Yeah, T2, R, and RC. So, from those three variables, there is an equation that doesn't involve all three. It involves two of them, but these are just things that we know at this point that are related to state 3 in a way, right? Because state 1 is not really related to state 3 in solving for things. So state 2 is. So we have an equation now for the cutoff ratio. The cutoff ratio is found by doing T3 over T2. But since we already know the cutoff ratio, we then solve for T3 because we know T2. And so, since we find, now I think we find T3 to be, I think it's 3005 or something. Pretty sure it's 3005. Childish Gambino. Times 2. Yep. 3005. And so what this gives us is now we now have something at state 3, which means we can find a H3 and a VR3. And that's important for trying to fix the other states in the problem, right? Because we have to know something about other states before we can solve them. So here we are. We now have something for state 3. We have 1, 2, and 3 done. And so this is just, reiterating what I just said. You use the table to solve for all the state values. And I think, so let's see, H3 comes out to be, I know I have to pause here because I have to find it in my notes. 792.146. And these are mostly interpolated values. I think I maybe guess on like one of them in a future problem, but I'm pretty sure I interpolated every one of these. So they're pretty close to right on the money. And so you get those two values. VR3 is 1.1738. And so VR3 is then used to find the next state, similar to how we found state 1 to 2, but only it's a little different equation instead of just using the compression ratio. And so our goal here is to find a value at state 4, to fix state 4, and stem from that. And so state 4 is the exhaust stroke. And so we know a couple of things about this state. Well, we know things that are related to it. How about that? Related to this state. We know T3. We know R. VR3. And we know RC. So from here, some things we can use. We obviously can use relative volumes, so VRs. I'm liking using fancy words like therefore. Don't want to distract you with the $5 words here, but VR4 over VR3 is equal to R over RC. I think I paused here to make sure I was right. Oh, it's the other way around. Yes, of course. These strike again. See, I wrote it, and then I thought about it for a second and go, wait a minute, that doesn't make sense. So you just catch yourself catch yourself writing it, and if you think it isn't going to make sense, like for instance, is the relative volume is going to go higher than what it was before on like the smaller volume, then yeah, you should probably change it. And so from there we have VR4 to be equal to VR3 divided by or it's R over RC, but then whenever it comes over, it flips. And so as you can see, VR4 is equal to a multiplier or it's VR3 times 8. So your VR got, it changed by, it got larger, which makes sense, right? You shouldn't have VR4, the bigger volume, being smaller than VR3, the smaller volume. It doesn't make sense that way. So I guess that's how I think about it, and that's how I keep catching myself, because I can't remember an equation to save my life. So just, if you can't remember the equation, just know the relationships. How about that? And so from that, we can now find all the state 4 variables. We can find temperature of 4, H of 4, and I think that's all we need here. I'm not sure you even need temperature 4, but I found it just because I wanted to prove that I could. To all the doubters out there. And remember, in the diesel cycle, since it almost caught me earlier, 1 and 4 use internal energy values, U values. 2 and 3 use enthalpy values, H's. Something to note, because if you mess that up, you'll have a kind of a weird number at the end, or you'll get something different when you try to start solving for efficiency of the cycle. So now we have the solution to the problem. These are the questions that are being asked in this problem. I think the first one is heat addition. But halfway through, I think I realized that this was going to look really bad, and it was going to look like Aladdin or something. So I was like, maybe we should get out of here. And I think I was also confused on how to spell addition. So heat added. See, you could change things. Similar words. Yeah, heat added into the cycle. So yeah, I don't know. Yeah, I had one of those moments where I knew how to spell it, but I also didn't at the same time. I'm sure you guys have had that too, so try not to crucify me because of that. So, yeah, and then I forgot the units anyway. In BTUs per, I think it's just BTUs, yeah. So, for this one, Qn is equal to H3 minus H2 times the mass. But if you remember correctly, we do not have a mass for this question. It did not give us one, so we need a mass. Now, how do we find a mass for this? Well, I think we have to use the ideal gas law at state 1, because state 1, they give us a lot of variables that we haven't used yet, if you haven't noticed. They give us, I think, volume, pressure, temperature. So those are all the key ingredients to make a mass in the equation. And so this is just me writing it out. And so mass is equal to P1V1 divided by RT. So here's where the units start coming into play. Remember, we have 14.2, this is PSI, times 0.5 feet cubed. Maybe. Oh, I forgot to put the units down. Huh. Man, I gave you guys something special, didn't I? Okay, so 14.2 PSI times 0.5 feet cubed. and this is divided by. Remember, since we're doing this on a mass basis, you have to change the ideal gas law, or the ideal gas constant, to an R, not an R bar. So 1545 divided by 28.97 times temperature, which is 520 Rankine. And I think there's also a conversion here. You have to get feet, or you need to get this into just pounds. So we have to cancel the feet cubed. So it's multiplied by 144 on the top. And I think, yeah, just inches squared. I think that's it for now. Because there's no BTUs we have to get rid of. So I think that's what you get rid of. Because there's a foot on the bottom that comes up as well. And so you end up getting 0.0368. Basically, when it comes to English units, you just need to let the units carry you through the problem, because English units suck. We all know that, right? They're not as fun. They're not as, I guess, easy to use as SI. So we have to make do. But if you just write out the units and let them cancel each other, and it'll get you to the right place, hopefully. And so now that we know the mass, we can find Qn, which we have as 15.58 BTUs. And here come the boxes again. As you can see, I completely went away from circles. I wasn't ready for them. Oh wait, did I? I think there was one on the last page. Huh. I'm mixing them. Alright. So now we're looking for the maximum temperature in the cycle. Which, if you know about the diesel cycle and Otto cycle, I guess, maximum temperature is always right after the heat addition. Heat addition happens between 2 and 3. So you would assume that after heat addition is state 3. So we know that T3 equals Tmax, which equals 3005.02. Hold up. And then the thermal efficiency of the cycle is one of the, part C. Thermal efficiency of the cycle is 1 minus Q out over Qn. But I think I changed this equation. I don't think I used 1 minus Q out over Qn. See if I remember correctly. I think I just use work cycle over Qn. Maybe not. Yeah, okay, I keep it. So it's 1 minus U4 minus U1. And as you remember, Q out is the exhaust stroke, and the exhaust happens between 4 and 1. And so it's the heat difference, or the energy difference between 4 and 1 is what left, right? And then the bottom is Qn, which is just what we talked about, the heat added. And this is me trying to find the answer, which comes out to be 56.5%. Ooh. Boxes again. Maybe. A little bit of a wiggly box, but that's alright. So, now part D, if that is a D, holy, that's pretty bad. Alright. So now we're looking for the mean effective pressure. This is the most complicated part of these cycles. This unit cancellation gets a lot of people. It got me pretty bad today whenever I was doing this. But we'll see if we can work our way through it. Let me pull out my notes. I might have to explain this one. Okay. Which is, so mean effective pressure is work cycle over volume 1 minus volume 2. So this is basically just I guess the mean pressure of the cycle, I guess you could say. I'm not really sure exactly like what it is denoted by. I'd have to look that up. But or like what it means exactly. I mean, you could just kind of read through a mean effective pressure, so the most effective pressure in the cycle. I'm not sure. But we know work cycle, right? And we know volume 1. Volume 1 was given to us in the question. And work cycle, we just kind of, we have all the information to find, right? So I'm going to do that really fast. Now I'm looking through to find the mean effective pressure. Because I'm kind of confused as to like what it actually is. I don't want to say something dumb. You know what I'm saying? And so from this 15.58 minus 6.78, I think it comes out to be 8.8. Something to that effect. Right? And so, since we now have the work of the cycle, okay, so the mean effective pressure is the theoretical constant pressure that if it was on the piston during the power stroke, it would produce the same network as actually developed. Okay, that's fun. Fun fact. So mean effective pressure is work cycle over V1 minus V2. But in this, you could find V2, right? And you get the same answer, but you don't ever need to, because V1 minus V2, that can be changed. If you pull a V out of it, pull a V out of the equation, you get V on the outside times 1 minus V2 over V1. It's an algebra, I guess, principle. And so, as you can see, you get that right there, 8.8 divided by 0.5 times 1 minus 1/16, 1/16th, which is 1 over the compression ratio, if that wasn't clear from the equation. Because V2 over V1 or V1 over V2 is the compression ratio, so V2 over V1 is obviously the inverse of that, flip. And now these are the unit cancellations you have to do. 778 is BTUs, and so 8.8 on the top is in BTUs, so it's cancellation, BTUs down, times 778 turns into pound force per foot, and then the bottom is in volume, is in feet cubed. Yeah, feet cubed. So you have to do inches squared, which is feet, you turn it to feet squared, or feet squared to inches squared, and then you end up getting, through some cancellations, you end up getting that right there. It'd be a lot. I kind of realized the video was going long, so I messed up. I kind of didn't want to write out all the units, but write them out and you'll find that it equals this. And so this is the end of the video. Yeah, the last part, maybe not the best, but that's all right. Hopefully you learned something, and see you next time.